Hi guys, it's Mrs. Grady. Time for us to take a look at kinematics and take a look at deriving some equations we can use to make things a little bit easier. We're going to start actually by going back to the lab with the batteries. All right, so hopefully you can read this. There we go. So the battery lab asked you to roll those batteries down the table, asked you to prove that they were accelerating. And what most of you came up with, first, we started with a position time graph, and you ended up with a top opening parabolic shape. Okay. After that, most of you straightened your curve out by squaring the x-axis, getting. I doubt that's where your y-intercept was. Sorry, I just slipped there for a minute. But we have a linear trend there, and a trend line that actually the slope ended up being the acceleration. And I could tell that based on the way that the units worked out, right? It was either meters per second squared or centimeters per second squared, right? Depending on what you used to measure. Okay. So that being said, um, what about the shape of this graph allowed us to realize that the object was accelerating? Well, if you figure that the slope of this graph is equal to the velocity, and you can see that the velocity is changing, that's our classic way of saying something is accelerating. It is changing its velocity. But that's not necessarily a mathematical reason in order to do that. And in class, so one of the things that I brought up was, well, okay, what if instead I asked you to draw a VT graph for this? Well, if we were to draw a VT graph for this, everyone in the one class in particular said, oh yeah, absolutely, it's going to look like this. It's going to be a nice little straight line because our velocity is constantly changing. So this VT graph, let's consider that our slope is going to be the change in velocity over time, which is our classic way of describing acceleration. Now, if you, and really almost nobody did anything with velocity during the battery lab, but I'm always curious to see because every group of people is different. There have been years where folks taking their data, they decide they're going to calculate velocity, and they calculate the velocity, and they have these set velocities. And really, if I push them hard and say, okay, now graph that for me, they end up with graphs that look like this. And then we have to take a look at what does that mean? Well, that would mean, really you're saying that, let's say that's from 0 to 1, that your velocity is staying the same that whole time. Well, that doesn't hold true. It was getting faster and faster the whole time. It kind of brings us to the average velocity versus instantaneous velocity argument, right? If we took the average velocity of all those steps and we put a best fit line through there, it magically looks like the graph over here on the left. Okay, so the idea of changing something from an average velocity to an instantaneous velocity has to do with the time, with changing the time that we're working with. So if we are looking at, sorry, I need to move my Chromebook a little bit. You're not going to be able to tell this, but it gives me a little more space to work, and hopefully it wasn't too noisy. All right, so if we end up trying to slice time in half, that naturally leads us to calculus. So what we're trying to do is take a slope, say from here to here. We say, well, that's not very accurate. Well, all right, what if I took it from here to here, or from 1 to 2? Well, that's better, but it's still not as accurate. What if you cut it in half and you cut it in half again until ultimately you end up with these teensy weensy slices of time? Your time approaches 0 seconds, right? That's where we start talking about taking that instantaneous velocity, taking the slope of just one spot on that graph. And how do we really do that? Well, what we're doing is we're taking a derivative with respect to time. And we're going to do a bunch more with calculus soon. So if this is like, what am I supposed to do with this? No worries. We're going to take care of that soon, just not today. All right. If we take the derivative, and you've probably seen it more like this, right? X prime t, same thing. That's going to tell us the velocity. We're taking the slope. Basically, we're taking a slope of a line. We're just taking the slope of a curved line. And if we were to take two derivatives, the second derivative of that position time graph, we would end up with the acceleration. And one of the interesting things is to look then at if you took the second derivative of this graph based on the curves that I asked you to print out, and then compared it to the slope that you got for this graph, it's curious to see how similar they are. All right, but we don't have to get too far into the calculus just yet. Just realize it's coming. There's a little foreshadowing there. English word. We can use English words in physics too. All right, but we are going to actually come up with some equations to work with. And the reason we need that is because time is our enemy when we're trying to figure out physics problems. We need something that's a little faster than plotting a graph all the time. Works great, but man, it's time consuming. So we need something a little faster so that you're not doing your homework for 7 hours, right? That's kind of the plan. So what we're going to do is come up with 3 equations that will help us in all of our little situations. But again, I don't like just throwing things out there without any context. If we start with the graph, we can actually derive these. You will not be required to derive these every single time. You also are not required to memorize the equations, although I do find that most folks do because we use them so often. But I do suggest that at minimum you put them in your calculator once we get them there, okay? Because you don't want to be without these, and you are allowed to use your calculator on all parts of the AP exam. So put stuff in there. Put all the stuff you can in there. Go ahead. All right? So anyway, acceleration. Acceleration is the slope of the line. So that's going to be the change in velocity over the change in time. To be fair, most of the time, our initial time is 0. So this is often simply written like this. Okay, I'm going to rearrange it, get rid of the fraction, and then I'm going to expand this. Now, anytime you have a change in velocity, it is always going to be final minus initial. So final velocity minus initial velocity equals AT. That's not how you're going to see it in a textbook. You're going to see it like this. There's your first equation, and it's coming from the slope of the line. Easy peasy. My second equation, we're going to apply it. We're going to look at that graph, but we're going to do it a little bit differently. We're going to start it actually here, right? And so our initial velocity is going to be here, and let's say our final velocity is here. Oh, sorry. I thought I could go off the page, but apparently no, that is forbidden. Okay, so let's figure we're looking at, oh no, sorry, hang on a minute. Let's erase. Let me redo some of that. Oh, that is so slick. I certainly enjoy a good technology program. Let's try that one more time. Okay? We'll start it actually from 0, but let's figure I'm going to go from VI to VF. All right, this is V sub 0 right here at the origin still. So here to about there. I'm going to work with the other quantity that is so important for us. Slope is 1, area under the curve. That's our other one, which really what I mean by under the curve is between the line and the horizontal axis. And that can be in the first quadrant, the fourth quadrant, doesn't really matter. On a velocity time graph, the area under the curve is displacement. You have to know that. So put it in your memory banks. You need it. So what I want to do is find the area under the curve for this lovely looking trapezoid. Now, I don't remember trapezoids, I'm not going to lie. So I'm going to break it up into a triangle and a rectangle. So what this is saying is that delta x is going to be equal to, let's call that one A, let's call that one B. It's going to be equal to A plus B. Okay, let's figure some of this out. A is a rectangle, so that's going to be base times height, and B is a triangle, so that's 1/2 base times height. So what are we looking at here? The base, oh, I probably should label that horizontal axis. I'm sorry. That's time. So that's going to be the change in time as the base, and the height here is actually the value VI plus 1/2. Let's do the base of the triangle. The base of the triangle is going to be delta T. The height of the triangle is going to be the difference between VF and VI. That's delta V. Okay. Now, what I'm going to do is I'm going to use this. I'm I'm going to use this relationship right here. Actually, this relationship, I have it in just the right format right there. And I'm going to put AT in for delta V. I'm just going to move stuff around here so it looks a little more like what I'm used to seeing. Now, why did I take out the delta? I realize in this case that we are looking at where the initial time is not zero. But I want to put this in a format that if you were looking in a physics book, you would see it. And delta T is implied, but it's often not printed that way. So I'm just going to drop it. Or maybe you could just call me lazy. I don't care, whatever. All right, so AT is what I put in for delta V. And then there's my other T. Now, if I simplify this, I'm right at the bottom of my page. I don't know if this is going to work. We'll see. 1/2 AT squared delta X. There's my formula. That's my second one of the big three. All right, it comes from using that other quantity from the graph that is so important to us, the area under the curve. Okay, so the first one, VF equals VI plus AT, delta X equals VIT plus 1/2 AT squared. Those are the two. Now, my third one is actually an algebraic combination of those two. So let's consider this. In this first equation up here, of all the variables, I am missing delta X here. There's no delta X in here. And down here, I'm missing VF. Sometimes these things are hard to measure, right? If you were doing an experiment or you're doing calculation, you're missing some information. Each of these three equations misses something in particular. Delta X is one, VF is the other. The third one that is particularly helpful to us is time. There we go. So we are going to write a third equation that does not have time in it because sometimes it's just a very short period of time. It's hard to measure. So what I'm going to do is I'm going to take both equations and I am going to substitute one into the other. That is something that we do a lot of here in good old AP Physics. And what I'm going to do is rearrange this one and I'm going to substitute in for T and get it to drop out. Okay, rearranging that for T would have been a mess. So let's move things around, move over the VI, divide by A. That'll give me T. Now over here, I'm going to substitute it in, and it's going to be a mess at first, but hang in there. Trust me, this is going to be elegant at the end. So VF minus VI over A plus 1/2 A, and oh dear, I'm going to have to go down here. That's all right. Squared. Okay. Let me rewrite that all the way down here. I probably just should have written it there in the first place. What was I thinking? Whoops, that's not right. Sorry. VI over A 1/2 times A VF minus VI on T and squared. Now, I'm going to avoid this stuff for just a few minutes here, okay? Because I know that's going to be an ugly mess. For sure. That is going to be, oh, I wrote that wrong, didn't I? What am I doing? That's an A. Sorry, it's not a T. If you were screaming that at your computer. No, I heard you. I fixed it. Okay. Now, for this one, it's up to you if you want to distribute this right away, but you can. VIVF minus VI squared over A. This one is a little tougher because we're trying to square it. And you know what? Honestly, all these fractions, they are so rough, right? So you know what I'm going to do? Let's just do this. Let's just do this to make it easier to see, right? We can do that. And then look, this one's going to cancel with that one. Why am I doing this? Because I want to get rid of those fractions, man. Fractions are stinky. You know, they just make, I don't know, whenever I make a math mistake, it always seems to be with fractions. I don't know. Maybe it's just something I just can't handle it, right? So I'm going to put the 2A down there. If I want to get rid of the fractions, what should I multiply both sides of this equation by? I should multiply both sides of this equation by 2A. And that will get rid of my fractions on top and bottom. So if I do that, here's what will happen. 2A delta X. Here I'm going to get 2vi vf. The 2 sticks around, but the a's cancel, which is nice. Minus vf minus vi squared. Now maybe you're thinking, well, that doesn't look that much better, but at least there's no fraction. Now I'm going to do the whole FOIL thing here. And I promise, spoiler alert, this is actually going to be very elegant at the end, and it's not going to be as messy as it looks once I do this FOIL. So just hang in there. Okay? So what do we have? Oh, where did I get a negative from? Good grief, Grady. I was just wondering, where does that negative come from? I'm just being silly now. All right, so vf squared minus 2vi vf plus vi squared. That's my expansion. Now let's consider this. Look at that. Goodbye. See you later. And now we can condense the rest. Oh, look, here's a negative 2vi squared, and here's a vi squared. So that's going to simplify as well. So good for me. Negative 2 vi. That's not what I wanted to write. Sorry. I wanted to condense that. Negative vi squared plus vf squared. Ooh, this is looking pretty good. Now we're pretty much there. That is a lot simpler than it looked at first, but it's not how you're going to find it in a textbook. So I'm going to rewrite this and just move things around so that you can see the typical format of this equation. Vf squared equals, we usually move the vi squared over, make it positive, plus 2a delta x. And that, my friends, is the 3 of the big 3. That's the third one. This one is missing time. We didn't have much time in class. Speaking of time, we didn't have that much time in class to do a bunch of practice problems. We will, just not yet. But this is the derivation of the big 3 kinematic equations. This is really kind of critical for us. I'm going to move to one more page over because I want to write this in big letters. These big 3 equations are really helpful. We're going to use them all the time. We're going to practice our problem-solving skills, pulling out the variables we know, solving for the ones we don't. However, there are limitations to using the big 3. All right, the limitations. You can only use the big 3 kinematics equations. Equations. If acceleration is, notice I'm doing all of this emphasis here, is constant. You have a constant acceleration. There will be examples in this class where we do not have constant acceleration. Not that we have like fancy other formulas we have to learn, but we do have to realize where we cannot apply just using a quick kinematic equation to solve whatever problem we have. We have to get creative and use other methods because the acceleration is changing. And so these do not apply any longer. All right, so those are the big ticket items from Friday, August 30th. Hopefully this is helpful to you. And let's see if I can figure out how to turn off Screencastify. Thanks for joining us.